Hello, everyone. On Monday, when I gave lecture, I don't think it was the best lecture I could have given because the slides went kind of out of sync. And I think some people were generally confused about a few of the diagrams. I've gone ahead and remade the slides. If you understood lecture on Monday, you don't really need to keep watching. But if you didn't, or if you were confused in any way, or if you didn't watch it, this is a lecture we'll be uploading so that folks can hopefully get a good grasp on index files and B+tree refinements. So the general characteristics of an index basically are that you're going to have some issues to consider in just about any index structure. Firstly, you'll need to wonder about query support. What class of queries does the index allow? Next, you're going to have to also deal with your choice of search key, which affects the queries for which we can use an index. You're also going to have to think about the way that the data is stored on disk. Is it intermingled with the index where the data is directly in the leaves of the index, or is there a pointer to the data from the index? If the latter, well, is the data on disk laid out sequentially in sorted order, or is it random? Lastly, what types of keys are we using? Are we using variable length keys? Are we using fixed length keys? We need to figure out these trade-offs. And using that, we can build a type of a cost model. Now, before I do that, let's talk a little bit about what our indexes are for. Now, we usually use indexes for basic selections like equality and range selections. And this is what B+trees provide. And this is what we'll be focusing on this class. Your textbook may mention something called linear hash indexes, which are really cool and they're very good for equality searches. They don't cover range selections, and we won't be covering linear hashing in this class, but they're pretty cool anyways. Now, other kinds of indexes do exist in modern DBMSs. You can support more exotic selections like a 2D box or 2D circles, which are good for maps or geolocation. N-dimensional indexes like R trees and KD trees also exist, and you could use indexes for near neighbor queries as well, depending on the type of index that is there in the DBMS. We won't be going too much into these, but it's nice just to know that these things exist. Not because we'll test you on them or anything, but really just because they're kind of cool to know how people actually do things in real life. Now for today, we'll focus on traditional 1D range and equality search for B+trees. So the first thing we need to figure out with the B+tree is what is a representation of data here? Are we storing the actual data in the B+tree, or are we storing a pointer to the data? In the last class, we had assumed for simplicity's sake that we would have a pointer to the data. Let's go through the different ways in which data is actually laid out for a B+tree. And then we want to figure out how is that data stored? Is it sorted? Is it unsorted? Which is a way to say clustered or unclustered with respect to the key that the index is built on. And each of these things have a very big impact on performance. There's three basic alternatives for data entries in any index. Alternative 1 is by value. Alternative 2 is by reference. And alternative 3 is by list of references. What does that mean? Well, alternative 1, when we say by value, we mean that the record contents are stored in the index file itself. That is to say, the index file literally contains your table, your tuples. Remember something here. In any leaf node, or in any index node, actually in any node of a B+tree, the node is sorted with respect to the key that it is built on. So in this case, all these nodes are sorted, these leaf nodes are all sorted on the UID key. Now, in the past, what we had was we had pointers with each key. This is what we went through in last lecture. So for example, we'd have 2 and then a pointer to the record pointing to Joe as the record. We'd have 3 and then a pointer or a record ID that would indicate the record for 3 Jim. But alternative one is a little bit different. It's actually the simplest. This is saying, no, at your leaf level, just store the record itself. You're just going to have the data there. And that might be really good, you'll think. There's something that this allows us to do. It allows us to just get to the leaf level and our data is right there. And we didn't need to do any extra IO to go to disk and follow a pointer to fetch the record that was associated with that key. And so you might wonder, well, why don't we just do alternative one all the time? And the problem is, think about how this file is laid out. This file is basically sorted with respect to a certain key. If I have one file, I can't sort that file with respect to two different keys independently at the same time. I can't have a file that's sorted on UID and then preserve that UID sorting while also uniquely sorting on name. And so this leads to a problem. If all we knew was alternative one, we cannot physically have a way in which we can sort, or a way in which we can have multiple indexes on a file if all we have is alternative one. We can't have two alternative one indexes built on the same file. We would have to duplicate that file and build another index on top of that new copy of a file. And this would be a problem. Because now let's say I wanted to build an index on name. And so I would duplicate this and build an alternative one index on name. I'd have to sort a new copy of the file by name, build my index there. And now here's the problem. What if I wanted to update my table? Now I have to do updates to two different tables. Clearly, this is suboptimal. So people had this idea, well, hey, instead of just storing the data in our leaf nodes, let's store pointers to data in our leaf nodes. This essentially separates the index and the file. So alternative two came along, and alternative two is a lot nicer in the sense that you can have many different alternative two indexes built on the same file. Why? Well, in alternative two, you'll have the index file, and at the leaf level, you will have pointers. You'll have key and then a record ID pointer to the record on disk, as you can see from this diagram. And this is good because now your index is kind of disentangled from your data file. And so I can have many different indexes that all deal with the same file. They'll just have pointers to the data. So now that we've introduced this idea of indexing by reference, now this enables us to have multiple indexes for a file, regardless of what key the file is ordered on. See, because the leaf level of the index is actually sorted by the key, you can see 2, 3, 5, 7, 20, 24 at this leaf level. It doesn't matter how the data is sorted on disk. Even if it wasn't sorted according to the UID key, that's fine because these are just pointers to data, and that data can kind of lie anywhere. Because that data can lie in any order with respect to the key itself, this is good for us because we've essentially enabled a way to have fast lookup, even if your index is not, even if your file is not sorted on the data that you're trying to build an index on. This is a very important idea. And one thing that you might be asking as a follow-up though is, well, hang on, there's only one pointer per key. So if I had a duplicate key, if I had a bunch of duplicate keys, let's say, for example, that I had 15 different Joes in this table. Would I have to have 15 different duplicate keys? And the answer is yes, you do. And that is why some people have this thing called alternative 3, where now for each unique key, you'll have that key in the leaf node and a list of record IDs of matching data records. And this is much more compact than alternative 2. It does come with a caveat, however, that for very large RID lists, single data entry spans can actually go through multiple data blocks. And we'll go over how to handle that in a bit. But the idea here is basically for each key, you have a list of matching record IDs. So you can see here that, for example, the key 2 has 3 matching record IDs, 1, 1, 1, 2, 2, 1. Now, some people might be confused about the notation. What is 1, 1, 1, 2, 2, 1 actually meaning? Well, 1, 1 is a record ID. It says on page 1, fetch record 1. 1, 2 is a record ID that says on page 1, fetch record 2. That's the notation that we use. So what this value really indicates is where on disk is that record that is associated with this key. So like I said before, both alternative 2 and alternative 3 index data by reference. And by reference indexing is required to support multiple indexes per table, because without that, we would start to replicate essentially entire tuples. And that's just not something we would like to do if we can avoid it. That leads to complexity when you're doing updates. And so generally, if you can, you would typically like to not have it. Now, there are cases where you might decide to do this. There are cases, for example, when you want a file that's sorted on a key and then you want that file to also be sorted on another key at the same time. So you can't really do that with one file. So you're going to duplicate that file. You're going to copy it over, sort one file on one key, one of those copies, and sort the other copy on another key. Then if you need to do, for example, super fast range scans, you could do that with each of those different copies of the file. And we'll go over how to do that in a second. But generally speaking, that type of duplication is annoying, problematic, a little bit difficult to work with. And so indexing by reference is a super powerful idea that lets us now build indexes without respect to how the file is laid out on disk. And so here's another table that shows you how alternative 2 and alternative 3 actually work. So alternative 2, you can see that each key, regardless of whether it's unique or not, has a record ID associated with it, whereas in alternative 3, each unique key has a list of record IDs associated with it. For example, for Gonzalez, page 3, record 1, 2, and 3. For Hong, page 3, record 4. And you can see here there's far fewer keys in alternative 3 because we only go with unique keys instead of all keys. Okay, so I've talked a little bit about how data is laid out on disk. The truth is, though, that when data is sorted on disk, it actually makes a very big difference in performance. And a lot of the time, that sorting can be important for us if there's a key we're going to do frequent scans with or frequent lookups with. By reference indexes can be clustered or unclustered, and that clustering does not really refer to the index itself. An index will always have data sorted at the leaf, or keys sorted at the leaf level, but what an index might not have, if it's alternative 2 or 3, is that data to be correspondingly sorted on disk. Clustered means that the data is sorted on disk with respect to the key that the index is built on, or at least approximately sorted. You might have a couple of keys out of order, but for the most part, it's sorted. Unclustered means that the data on disk is not at all sorted with respect to that key. It's essentially laid out in random order, and the index is just there because it makes your life really easy for lookup. and for scans, but the index doesn't leverage any type of sorted order for the file itself. The file isn't sorted. And the index is providing you a structure with which to fetch data on a key, even if the file is not sorted on that key. Okay. One thing I want to go through briefly before I go over more details about clustered and unclustered indexes is that this is a different definition from clustering in AI. And it's just important to be wary of that distinction. AI clustering is very, very different from what we're talking about in this class. So what do these indexes actually look like when they're clustered versus unclustered? Well, this is a nice diagram that visualizes it. So to build a clustered index, we're going to first sort the heap file. And generally, we want to leave some free space on each block for future inserts, because that will enable us to insert keys nicely without having to reshuffle data across multiple pages. And your index entries here are going to direct the search for your data entries. This isn't like the case in which you had alternative one where your index entries literally contain the data at the leaf level. Now here, they're going to be like pointers for your data entries. So you can see here, let's say that I wanted to do a scan on these two nodes at the leaf level. How many pages would I read in on disk that correspond to these two nodes? Because when I get the keys here in these nodes, I have to also get the records associated with them. How many different pages would I be touching for each case? In the case of a clustered index, these nodes the file is essentially approximately sorted by the key that this index is built on. And given that the nodes themselves are going to be sorted with respect to each other, so for example, I could have 1, 2, 3, 4, 5, 6 as the keys here. I know that all of those records associated with those keys are going to be very, very close together on disk, because that file on disk is sorted with respect to that key also. In unclustered, that's not the case. In unclustered, even though the keys will be sorted at the leaf level, the records themselves will not be sorted on disk. And so 1 could be over here, 2 could be over here, 3 could be over here, 4 could be over here. And what that basically means is each page, each key could actually have its corresponding record on a completely different page, which means that at the end of the day, for a clustered index, I might only here read 3 pages worth of data from disk to fetch all of the records total associated with these two nodes. But in an unclustered index, because I have no guarantee about the ordering on disk with respect to that key, well, I would have to read both of these nodes and read 5 different pages on disk in some cases, because I simply cannot guarantee where data is, and it could be anywhere else. It could be, sorted. It could be put randomly in disk at any position. Like I said, the record for key 1 could be on page 1. The record for key 2 could be on page 5 or whatever, and that could lead to some problems in terms of speed. We'll go over a little bit of what those trade-offs are. But basically, what that means is in a clustered index, you can generally assume that keys that are close together in value will also have their corresponding records be close together on disk, often on the same page or on pages immediately next to each other. In unclustered indexes, keys that are close in value, you don't know anything about where they are on disk. They could be on completely different locations on disk, page 1 and page 100. And so you have to typically be careful when you're doing your IO calculations for these and building your cost model. One more thing about clustered files is that the blocks at the end of the file might be needed for inserts. And so the order of the data records is going to be close to, but not identical to, the sorted order. So for example, sometimes if I want to insert another value in here, another key in here, I might find, oh, well, there's no more space in this page. That's fine. I'll just add on a page at the end and I'll just write it to that, or I'll just take the page at the end of the file and I'll write my new value to that. And you might think, wait, doesn't this break our sorted order thing for clustered? And yeah, it does. But the truth is, it's still approximately sorted. There's only a couple keys out of order here or there. And so generally that's still good enough for our performance. So really speaking, at times then, as the file gets more and more disorganized, you might want to do some housekeeping to resort it and maintain and preserve that clustered structure. And so some pros of clustered indexes is that they're very efficient for range searches, and there's locality benefits that you enjoy. You can imagine why they're efficient for range searches because, if I'm looking for a range of records associated with a key range, if I'm looking for the records associated with the key range, I can guarantee that those records are close together on disk if the index is clustered with respect to the key that it's built on, which is good because if those records are close together on disk, many of them will lie on the same page and I'll have to touch fewer pages to read in all of my data. But this is not necessarily the case with unclustered indexes. In fact, it's almost never the case. So even though two keys are close together lexicographically in unclustered indexes, they could be in radically different positions on disk. Clustered indexes also support certain types of compression. We can briefly touch on that too. But the cons of clustered indexes are there, and it's that they're more expensive to maintain, and you might need to periodically update your heap file. Heap files are also typically usually only packed to about 2/3 capacity to accommodate inserts, and so they may take up a few more pages as a result. Now that's generally okay because of sequential locality benefits, but it is something to be cognizant of. Okay, let's talk about variable length keys now. So far, we have been using integer keys, but we want to find out what would happen to our occupancy invariant if we had variable length keys. See, so far we had said, let's assume a B plus tree has order D. What does that order D mean? Well, it means, if we had to put it in the simplest possible terms, that the key can at most hold 2 times D entries. And the occupancy invariant says that outside of the root node, all nodes need to hold at least D entries. And when you split, you'll have D on the left, D plus 1 on the right for a leaf node. And when you split an inner node, you'll have D entries on the left, D entries on the right. You'll push up the middle key. Remember when we went over that last lecture? Well, it turns out that's all well and good for when I know exactly how many entries will fit on a record or on a page. For example, if I have an integer, I will always know that I could fit maybe 2,000 keys on a page. But if I have strings instead, that doesn't really work any longer. If I have strings, each of these strings can take a radically different length. So now I can't guarantee, for example, that a page can hold 2,000 strings because it's, well, what about the string size? How big is a string? What are we dealing with here? And so let's redefine our occupancy invariant. Order D does not really make sense with variable length entries. Different nodes will often have different numbers of entries. And index pages will often hold many more entries than leaf pages. So in practice, we're going to use a physical criterion, which is at least half full. And this is going to be measured in bytes. Basically, it says if the page is at least half full. And that's our new occupancy invariant. We're going to move from the integer space of order D or stuff like that to how many bytes does it take up physically? How many bytes does the data on our page take up? How full is this page with respect to the number of bytes consumed? Now, many real systems are even sloppier than this because it's really just about performance in the real world and optimizations and shortcuts you can take while still maintaining your properties about as well as you can, but we don't need to worry about that. So let's go over prefix compression really briefly. This isn't going to be tested or anything. It's just kind of cool to know. One of the things with strings is that they often share prefixes. And so we can take advantage of that prefix compression. We can take advantage of that prefix structure to compress keys. Let's say that I wanted to add in the value Sarah Lee to this array of Sarah Manning, Sarah Zhu, Sarita Adbe, and Saramanda White. How would that work? Well, what if we compressed here by determining the minimum splitting prefix when we're copying up from leaves? So at the leaf node, I'll enter my data entries, right? Sarah Lee, Sarah Manning, Sarah Zhu, Sarita Adbe, Saramanda White. That's all well and good. But when I'm going to split, I'll need to determine the minimum splitting prefix, and I need to copy up. So here, the middle key was Sarah Zhu. What's the first prefix? What's the minimum prefix that will differentiate Sarah Zhu from Sarah Manning? It's Sarah Z. And so that will be copied up to the index level. There's another cool thing called suffix key compression. All these keys are going to, a lot of these keys can sometimes have a large common prefix. And we can move that header. We can move that prefix to the header and leave only a compressed form of the suffix next to a pointer instead. So for example, here, all of these have the common prefix SAR, S-A-R. So you can move that to the header, and you can see here now clearly we've saved ourselves a lot of space because we moved away the SAR, and very nicely now we are left with something pretty cool. Each of these entries now takes up far less space in a node because we moved the common prefix to a header. Okay. So once again, this is just something cool. Don't worry about it. It's not really going to be tested, but it's nice to know anyways. Okay, lastly, to wrap up this lecture, I want to talk a little bit about costs. Joe Hellerstein's excellent videos have a bunch of formulas. If you really need to, you can rederive them very easily. They're very intuitive, but we don't want you using formulas in this class unless you really need to. We want you to count the IOs yourself. So let's walk through some examples of how to tackle problems with alternatives 1, 2, and 3. Specifically, really with alternative 2 and 3, and mainly alternative 2, if I'm being honest, because that's the simplest way to go about a presentation and how you're going to tackle these problems. Okay, so let's maybe have some assumptions we'll throw out there. Clustered index with 2/3 full heap file pages. Your heap file is initially sorted. If it's clustered and your index is going to be static, you're not going to have too many insertions or deletions. Okay, for a full scan, do we need an index? The answer is no, we don't. And the reason we don't need an index is because the cost is simply going to be the number of the pages in a file for a full scan anyways. We're reading all of the records. If we're going to read all the records, who cares about an index? Why do I need to actually use an index to navigate through the different records when I'm just going to end up reading them all anyways? I could just load the file into memory and just read the entire thing. So for full scan in a B+ tree, you actually don't need an index. You can just, the cost will just be the number of pages in the file. There's no need to use the index. The file exists there. Okay. How many IOs would you need to retrieve the record for UID 3 here? Let's think through it. Let's do a search for 3. 3 is going to be less than 17, so we're going to go to the left. 3 is going to be less than 5, so we're going to go to the left. Okay, now we're at our index node that contains the key 3. This is alternative 2, so we're not quite done yet. We're going to then follow the pointer, the record ID, to disk, page 1, record 2. We're going to load in page 1, and now we have our record. How many IOs did that take? How many pages did I touch? I touched 4 pages, the root node, the next index node, the last index node, which is the leaf node, and then the data page. And in general, the way to tackle these questions can often be how many index nodes in total do you touch, plus another IO to read the associated data pages if you've just had one match. Okay, now let's try to tackle ranges. Let's talk about how many IOs you would need to retrieve a UID range. For example, 320. In this case, what would we do? Let's go through it. Let's find the beginning of a range. 3. Go left. So we're at this node now. We've touched 3 nodes so far. We've had 3 IOs. Okay, so 3 IOs. And some of you might be wondering at this point, hey, you keep using this term IO. What's an IO? Remember, an IO is basically reading or writing a page from disk to memory, reading a page from disk to memory, or writing a page from memory to disk. That's an IO. It's when you read a page from disk to memory or write the page from memory to disk. That unit of transfer is an IO, and they're dealt with in pages, in whole pages, as we went through in the disks, files, and buffers lecture. Okay. So I've read in the root node, I've read in this index node, I've read in this last leaf node here, this first leaf node. I've had 3 IOs so far. Now, I've begun my range at 3. So I'm going to fetch the associated record. I'm going to load in page 1 into memory. There we go. Okay, I've had 4 IOs so far. Now, I'm going to continue my range search. I'm going to go to the next leaf node, 5, 7. Okay, so I'm going to pull in the data associated with keys 5 and 7. That's on page 2. So I'm going to pull in page 2 now from disk into memory. That's another IO. So far now I've had 1, 2, 3, 4, 5, 6 IOs. Okay, now I'm going to continue my range search. I'll go to the next node, which has 20 and 22. Oh wait, this is really good because my range has just stopped here. Now I know the ending of my range. So I had this 1 extra IO now to read in this leaf node. I'll only need 1 more IO to read in the data page that corresponds to key 20, which is page 3. I'll read in page 20, or I'll read in page 3, and now I'm all good. How many IOs in total did I have? I had 8 IOs. I had 3 IOs to get to and read in the first matching leaf node. I had to read in the 2 more leaf nodes that matched. And then I had to read in the 3 matching data pages, the data pages that contain the records of the matching keys. So the total will be 3 plus 2 plus 3 equals 8 IOs. The rule for clustered indexes is generally that you're going to have 1 IO per matching page of records. This is because when I'm doing range scans, for example, once I pull in the data associated for 5, well, 7 is right next to it. So 7 will often just be on the same page as 5. So I don't need to do a separate IO to pull in 7's associated data record. Okay, now what if we complicated this a little bit? What if we had unclustered alternative 2? So it turns out this gets a little bit more annoying. I'll still read in the same number of index pages, which is 5, 3 leaf nodes, 2 inner nodes. But now each of these records is actually lying on a different page. Each of the records associated with these keys is actually lying on a different page. So I'm going to have 1 IO per matching record. And so I have 4 matches here, and I have 5 index nodes that are read in. So I'm going to have 5 plus 4 equals 9 IOs to retrieve the UID range 320. Okay, so to wrap this lecture up, let's just briefly touch on some constant factors. Typically, you can assume you can do 100 sequential IOs in the time of 1 random IO. This is often why clustered indexes are very, very good. Now, for a particular lookup, you might ask, is a B plus tree better than a full table scan? And the answer is, if it is, it better be very, very selective. You need to visit around 1% of the pages for the particular lookup. Many times that might be the case. So B plus trees are very, very powerful and very useful for that reason, because if you think about how much data we typically get in an inequality search, it's not that much, or how much data we get in a range search. Well, sometimes if it's a small range, it'll still be a very low amount compared to the size of the entire file. But there are times when a full table scan is better, and that's typically if you have an unclustered index at one level, which would result in a lot of random IOs. And if you have an unclustered index and you're trying to scan a range that's like half or a third of the table, then sometimes a full scan might just be better. Sometimes though, B plus tree could be better than a full table scan, even for like a range search. And that's like if you have a clustered index, then you're doing sequential IOs at the leaf level, because like we mentioned, the data is sorted on disk with respect to the key itself. And so in sequential IOs at the leaf level, you're really just reading in the records in sequential order, even on disk. For example, 5, 7, and 8, the pages for the records that match with those keys are probably going to be very, very close together on disk. So your IOs will be sequential to pull those in. You could also use SSDs. They make those indexes nice, especially for read-only workloads, but not really going to go into that. Okay, so the summary is now we know how to navigate through, split, insert into a B plus tree, and we understand composite search keys, lexicographic order, and search key prefixes as we went through in the last lecture. In this lecture, we went through data entries and how they're stored. So alternative 1, which is the actual tuples at the leaf level, alternative 2, which is record IDs at the leaf level, and alternative 3, which is a list of record IDs at the leaf level. And we learned that if we want to have, if we wanted to have multiple indexes built on the same copy of a file, we would need something called referencing. We would need something called index by referencing, which is alternative 2 and 3. Okay. And we also learned now the difference between clustered and unclustered, which, by the way, only applies to alternative 2 and 3, because clustered relates to how is the data sorted on disk with respect to the key that the index is built on. Well, in alternative 1, the table is literally just part of the index in a sense. And so you already know it's going to be sorted. So it doesn't really make sense to say it's clustered. I mean, it's exactly sorted, and it always will be because of the property of an index in alternative 1. Okay, couple of brief addendums. Some people might ask, is it possible? You have said in lecture that it's not possible to have one copy of a file and then have an alternative 1 index on a key there, and then have an alternative 1 index on another key without duplicating the file. Can I have one alternative 1 index and then an unclustered alternative 2 index on the same copy of the file? The answer is yes, that I can do. If you think about it, the reason is because at the leaf level, I'll just have my records, right? I will just have records at the leaf level in those pages for alternative 1. And they'll be sorted with respect to some key. So you can essentially think of it like I have a sorted file at the leaf level. And so for alternative 2, if I want to build an index on another key, I could do that, and I could actually just reference the leaf level of the alternative 1 index. But of course, if I was to do that, then without duplicating the file, then I would have to build an unclustered alternative 2 index if I wanted to reference anything else. And that's the power behind alternative 2 or alternative 3. You can index by reference, because I can then reference where records would be on disk without worrying about whether they're sorted or not.